Hello everyone. Today we are going to look at polynomial regression. So before we move to polynomial regression, I believe you are already familiar with linear regression, but let's just do some quick recap so that to help us understand what we are coming to do. So with linear regression, the algorithm finds the best fit straight line relationship between the two variables. Right, that's linear regression. The statistical method is then used to predict the outcome of the future event and is quite useful for predictive analysis. So this is a simple linear regression algorithm or analysis. So we can see here that this one, the data here, the model performed very well by it was able to draw a straight line. The model estimates the slope and intercept of the line of best fit, which represent the relationship between the variable. The slope represents the exchange in the dependent variable for each unit change in the dependent variable, while intercept represent the predicted value of the dependent variable when independent variable is what is 0. So this is the formula for linear regression. Y is our output is equal to alpha 1 plus alpha 0 plus alpha 1 x plus e. Okay, so why linear regression is so important? So I believe this one you are already familiar with it. Since it was simple prediction, widespread applicability, foundation for other techniques. Okay, so now we can move to what we are going to talk about today, which is what a polynomial regression. So a simple linear regression algorithm only works when the relationship between the data is linear, right? However, if we have a nonlinear data, linear regression will not able to draw a best fit line. So simple regression analysis fails in such condition. So we can consider the diagram below, which has a nonlinear regression. And you can see that the linear regression results on it, which do not perform well, meaning it does not come close to reality. So we can see the orange line is our linear regression. It's our linear regression one line. So this is the formula that we saw up there earlier. So situation like this is when we use polynomial regression. So in short, polynomial regression is type of regression analysis used in machine learning and statistics model relationship between one or more dependent variable features and a dependent variable, which is target, when the relationship is nonlinear. So it extends linear regression by allowing the model to fit a curved line, right, to the data rather than assuming a straight line, like which is linear regression. So you can see it here. Here our data, we can see that the model is trying to draw this line, a straight line, but it wasn't very good. But with with polynomial regression, it was able to draw the line. Okay, so we can continue. How does polynomial regression handle nonlinear data? So polynomial regression is a form of linear regression where only due to the nonlinear relationship between the dependent and independent variable, we add some polynomial term to linear regression to convert it into polynomial regression in machine learning. In other words, polynomial regression handles nonlinear data by transforming the input into higher degree polynomial terms, like, so we can see here, x raised to the power 2, raised to the power 3, etc. It can continue and continue, which still uses linear regression under the hood to fit the model. The equation of polynomial regression is something like this. So it is here. Y is equal to beta 0 plus beta 1 s1 raised to the power 1 by y1 beta 2 s raised to the power 2 plus, then continue to the nth number, which is the highest exponent in that particular problem of data. So which is where n is the degree of the polynomial. So polynomial regression related vocabulary. So here we can use this as an example. Right, so degree of polynomial is the highest power exponent, is the highest what power, which is the largest exponent in your polynomial. So here it is what it is 4 because s raised to the power of 4, s raised to the power of 4 here for 4. And the coefficient are this one, our numbers, right? So in each number 2 for it in our polynomial is a coefficient. These are unknown parameters that our model, or yeah, our polynomial regression model will try to estimate when trained on our data set. And then we have the leading term. The leading term is the highest power, which is 4s. So here, all of these are the leading term. All of these, this and this is the leading term because it has the highest exponent. And then we have the leading coefficient, which is still 4 because it's the highest number here. And we have constant term. The y-intercept, it never changes no matter what the value of s is. The constant term remains the same. Okay, so linear regression versus polynomial regression. So linear regression model assumes a straight line, which is the simplest explanation that we can give. Linear regression models assumes a straight line, which is y is equal to beta 0 plus beta 1 s plus e, where y is the dependent variable, s is the independent variable, beta 0 is the intercept, beta 1 is the slope, and e is the error term. This works well for linear data, but fails when the true relationship is curved. When the true relationship is what? It's curved, quadratic like. So when it is like that, then we move to a polynomial regression. So a polynomial regression model is used to describe a nonlinear relationship. The magic lies in creating new features by raising the original features to a power. For instance, if we have feature s, we will use a third degree polynomial. This is a third degree polynomial, right? Meaning s raised to the power of 3. Then our formula will include s2 and s3. And this is what gives curvature to a line. So these are also some of the advantages of using polynomial regression. It is flexible, it is interpretable, and they're easy to implement to like Python, scikit-learn, R and Hot, and Excel. Disadvantages: there's overfitting, right? Higher degree polynomial can fit more in the data, leading to poor generalization. Use techniques like regularization or cross-validation to choose optimal degree. And then we have this, then extrapolation works, and the fitting also. So these are my references. So now I think we can jump to Excel to perform some simple okay. So here we have a data that we are coming to use to visualize or how linear and polynomial regression differs, and what we learned earlier, the theory, and put it in a little bit of practice here. So this is our data. This is the marketing spend, a campaign, or market spend versus a conversion rate. So we have this data. Maybe I can draw, insert chart, recommended. We go to our chart, we go to scatter, and we select this one. Okay. So this is our data. We are visualizing the data. So I can add a trend line. So you can see our linear regression. This is our linear regression trend line. Let me add the axis. Marketing. Then we have convention. Rate. So this is going to be convention, marketing spend versus convention rate. So marketing versus convention rates. Okay, so if we go to trend line, more options, and if we select a polynomial with an order of 2, which is meaning uh, the highest exponent, right? As we learned here, degree polynomial. So this is a second order of 2. And we have, let me display the equation on chart and the R squared on also on the chart. So we can see here our model is performing very fine, which is 80%. But if we use the, let's say the linear, right? Let's try the linear regression so that I'll be able to understand linear, right? And let's say this one. So you can see that here we have 70%, 73%, and here we have 80%, which is not much different, but it's a lot of difference, right? And here we are using order of 2, so we can also modify it to, let's say 3 or 4, right? Let's try that and see. Let's say the order of 3. Order of 3. So the order of 3 we have 81.99. Then we have 82.21. I think the order of 3 is not bad, but our model is getting larger, right? We have, so now we are at degree of 3, right? Which is the highest exponent. It's not too bad, actually. So we can see 80% or 81%. It's just, let's say 10% increment or something like that. It's not bad, but you need 1.9, so close to 82. Our data, so we can copy this data. Let's copy it and then paste it here. We set our R square. So set a column, pi column, R square. So this is equal to this raised to the power of 2. Okay, so now we can go back and then do it again. Data analysis, regression. Okay, we select our Y input, this is our Y input, our X input, select both of them because we're using linear regression, sorry, polynomial regression, and then our output, I think output can be here, not bad, and normalize probabilities, and we see their plots. Okay, so with confidence level, say 95, 95, then let's see. So the regression input range contains numeric data. Okay, so let's say this. Very quick. What is this? Okay, so here this is our intercept, our s variable 1, and then s variable 2. So this is still having, which is close, right? Our R square is 80%. This which one? This one 80.97%, which is 80%, not too shabby, not too shabby. So we can try to predict some data. You can try to, let's say, predict. Yeah, let's predict this one and let's see. Let's predict this one and let's see. Do some small prediction. So our R square, I think is there already. We just have to write it down. So, okay. So here insert insert entire column. Okay, so you can say let's use linear. Just go for the linear prediction and polynomial predict, predicted. So here is our main data. Right? So with here, what do we do? With linear regression, this is the formula for finding the linear regression, which is equal to 0.0145 times x times x, which is this one, minus 5.2436. And so can drag it down and see. So this is our linear prediction, right? Basing on these values, we just using the value that it gave us. And with our polynomial regression, equal to what? 9e minus 0.6. So we can find it here. So equal to this variable. Let's lock it f4 and let's put it here times r squared. Don't forget, it says r squared. Where is our r squared? This one. We are not going to square it again because it's already squared, right? So r squared bracket close minus bracket open 0.117. Where is it? So this one is going to give us 7. So let's type it 0.0117. Yeah, plus x times x times x 250 bracket close, and then say plus 10, which is our r squared, right? Sorry, so now ask our intercept times this one. We can also log this one, the form, and then so this is giving us 37. So with this, we can see that our model wasn't able to perform very well using the linear regression, right? So we can see it here, which is not too good. But with our polynomial regression, our model was able to predict the values very well, because if you can see the data, it was rising and rising. But this one just say 31, 70%. With the polynomial regression, 37, 41, blah, 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 which is very good, which is very good. So we can also plot it on data to see. With that, I think let's try this data. This is our example 2, using the temperature, ice cream sales, temperature and temperature and an ice cream sale. So with minus 4 degrees, it was able to sell 41 units. Maybe there was a discount, who knows? Yeah, there was discount. So with this, we can also plot our data. Let's try to plot our data. It's in scatter, insert, commented, or chart, scatter, and then we choose this one. So, okay. If we add our trend line, you can see it is very, very bad. It is very, very. So this is, so if we go to trend line and we say, yeah, so trend line, okay. So here we can select the polynomial. You can see polynomial. If it is linear, you can see our model. Let's look at 30%. which is very bad. But if we select our polynomial regression, we can see which is 90. This one it was what? Dot 0.3, which is less than 1%. Less than 1%. But with our polynomial regression, we have what? 93%, which is fantastic. And it was even using order of 2. If we increase it, right? So I think 93 is not bad. Well, our model is getting more and more. I think 93 is not bad. Order of 2 is not bad. Look at this. Look at the difference. Look at the difference, which is enormous, right? So with this, these are like the best example or the reason why we use polynomial regression. So with this one, I think I can just insert them here. Insert entire one, and then we say temperature temp square, right? And then what do? We say equals this raised to the power of 2. Okay, so now what do? We just use our data analysis. Excel, we go to data, and then we go to data analysis, regression. So within regression, then we select. The first one is one input trace. So excuse me, because then this one is our okay X input. Our output, let's put it here. Okay, so let's put it in, let's see. So now we can see that it's the same thing, right? We are getting R squared, but 93%. Same with this one, using our scatter. So let's try to predict some values and see. Let's try to predict some values and see. Let's see. The weather was 5. How about that? Let's say 5. It's going to be 5, 25. And then this one is what we are going to predict. So let's try to insert an entire column. And then let's call this one poly predict or predicted poly predict. Bad name. So it's here. What can we do? We look at our model. Where is it? This one. So we say 1.9, so equals 1.829 with this one, right? And then we lock it, F4, 1.829 times R squared, so times 25 minus, so let's put it in bracket to, okay, minus bracket. But again, what do we have? 0.824. Where is 0.824? Let's type. If we select, it's going to select as minus. So 0.82468 times R1. So times R1 or X1 plus, so, oh, plus our intercept, right? Plus our intercept, plus our intercept. Let's see. So you could see, so if we select this, let's say 6, It is was performing very well. But if we use linear regression, because I don't know, but we can still try. Let's try it anyway. Let's try it anyway. Let's try it anyway. Let's try it anyway. Because v x is times x 5 plus this. Oh, oh, I see. It is enormous difference. It's less than 1%. But with our polynomial regression, we got to 93%. So with situation like this, where our model can a straight line, best fit line, then we use a polynomial regression. Okay, thank you everyone for your attention.